Welcome to the first video on chapter 34, which is all about electric current in conceptual physics. And we're going to be first talking about section 34.2 in your textbook, which is, what do you know? It's about electric current. So, the book first gives you this very simplistic definition of electric current that I'll lay out for you right now. The flow, sorry about that. The flow of electric charge. And that's pretty much what you need to know in terms of words. There's an equation that we'll get to express it mathematically, numerically, which I personally like better. It's a little easier to grasp. It's maybe for a math brain. I don't know, how you think, but that's the great thing about conceptual physics. But flow of electric charge is the first thing they give. I'm going to add one thing through conductors just to clarify, because I feel like some people always kind of lose sight of the fact that it has to be through a conductor. It has to be through a metal or something that conducts electricity through conductors. Sorry for the messy penmanship. Through conductors. Now let's first dissect this sentence and kind of look at the separate parts individually. So flow. First thing when I think of flow is a river, right? You have this river maybe. This is the banks of the river. And you have water flowing through it for whatever reason. But no matter what that reason, it's due to a potential difference. And potential difference can really be in any gradient, any medium that you want. Often in the river example, it'll be in height. So like a waterfall will flow from point A down to point B because there's a potential difference in height. Now when we're looking at electric charge, why does it flow? It flows because there's a potential difference in voltage. Okay? That's your potential difference here, but we're going to get into that a little bit later. Now let's dissect electric charge. Now we remember that as, hopefully you remember that from chapter 32 as the coulomb. That's the unit to measure electric charge, and that's essentially 1 coulomb is equal to the charge that 6.24 billion electrons have. So if you, at any given point, you're looking at 6.24 billion electrons, you're looking at 1 coulomb of charge. That's just a brief, charge is kind of like the electric force that an electron carries, the energy that it carries. Now, conductors are materials like metals. Those are great conductors because the electrons are loose and they easily pass their energy on to the next one, onto the next atom. Now bad conductors would be things like wood. Wood is no, because the electrons are very close to their nucleus. They don't want to give up their energy. They don't want to bounce around. They're not very excited. And also bad conductor, rubber. You'll see often appliances will have rubber handles. It's to protect you if there's any excess charge that comes springing back to your hand. Oh, rubber stops it right in its tracks. So now, that's your basic dissection of an electric current. And it's essentially the flow of electric charge that electrons carry. I'm going to kind of give this little section here, devote it to a diagram that I've been thinking about. It's not too complicated, but it's a diagram of a wire. Not straightest, but I'm going to make it kind of thick so we can really dissect it. Now, at any given time, we can look at this cross section right here, this section here, and we'll see a bunch of little electrons bouncing around. They're so excited. Oops, those are thicker than I imagined. So we have this cross section, right? And at any given time, you'll have these little electrons. I'm not going to draw the whole atom. I hope you know what that looks like. Bouncing around. They're really excited. They're kind of staying in their own area. They're bouncing to different atoms, but they're always losing and gaining energy, and they're always passing on charge. And these little yellow guys are obviously electrons. So if I take a cross section here and look at the section of a wire, if I see at any 1 second, if I see 1 coulomb of charge, so if I see 6.24 billion electrons, which isn't rare, mind you, because they're so darn small. I have seen 1 amp, 1 ampere of current. Okay? So that takes us to the next section, which is the mathematical way to express electric current, which is my favorite way. I'm going to try to make this video as concise as possible. So first we're going to dive right into the math. Current equals charge over time. Okay, I'm going to put time right now. But then to really specify it, we're going to use the units. Well, what's our unit for current? That's the ampere. It's called the ampere. Spelled just like that. You might recognize that from an amp, like a guitar amp. Well, and we know our unit for charge is called the coulomb. And we know our unit for time, well, the SI unit for time that we always use, le Sistema Internacional is SI. If you didn't know that, little fun fact, seconds. So C, A, and lowercase s. So we're going to abbreviate this to ampere. Ampere equals coulomb over seconds, or even more, A equals C over S. And I think that's a great equation to know. You should definitely memorize it for your upcoming tests and whatnot. And pretty much that goes back to that cross-section question that I was talking about earlier. If you have this cross-section of a wire, if I take a cross-section right here, okay, and I look inside this wire, if I look for 1 second, and I see 6.24 billion electrons, which would be easy because they're so darn small. I've seen 1 coulomb, right? And therefore, I have seen 1 ampere of current. Very cool. Very cool. So now I'm going to get a little mathematical for those that like that and those would be interested in that. It's actually not too mathematical, but it's interesting. It's kind of proportions. Well, we see that in this equation, amperes directly proportional to coulombs, charge, and inversely proportional to time, seconds. So if we were to double our charge, means if we were to go up to 12.48 billion electrons in one cross section, so x2, since these are directly proportional, our current would also go up by a factor of 2. It would go up by the same factor as the charge goes up because they're directly proportional. Now, let's say forget that I just did that, and let's see what happens. What happens if we increase the time, our viewing reference time, x2? Well, oops, that's a little more thick than I wanted it to be. Let's go, let's try a different color. Let's mix it up. x2. Well, since current and seconds are inversely proportional, now remember, seconds isn't going to change the coulombs because they're on the same side of the equation, of the equal sign, the same side of the equation. Seconds will affect the current though. If you multiply the seconds by 2, you're going to cut the amperes in half. So that's very interesting. There's kind of proportional things which we can test out. Let's say we have, I don't know, maybe 10 amperes equals 20 coulombs over 2 seconds, right? Well, what happens if I go up here and I multiply our coulombs by 2? Well, I have 40. So now I have 40, right? What's 40 over 2? Well, that's 20, right? So this would go up by a factor of 2. It would go up to 20. But what happens now if I were to, forget this, multiply this by 2, this would go to 20 over 4. What's 20 over 4? That equals 5. This went down by a factor of 1/2. The inverse, it went down by the inverse or the reciprocal of what seconds went up by. So that's my video. That's my spiel on electric current. I look forward to seeing you guys to talk about voltage sources, electric resistance, Ohm's laws, alternating, direct current, all of that stuff. So I'll see you in the next video.